Welcome back. In this series, I will show you how to create Vortex Induced vibrations simulations in OpenFOAM. And this is Tora. In the previous videos, I have shown you how to create the geometry, create the mesh, and how to set up the boundary conditions required for our simulation. For now, we will be choosing the right solver for our simulation, and we will be choosing the right numerical schemes and solution algorithms, and we will set up the physical properties of the fluid. So this is the general guideline for choosing the right solver, and it's only applicable for incompressible fluids, and I will cover the compressible fluids and heat transfer and multi-region heat transfer, etc. after later videos. But in this video, I will only distinguish between the incompressible solvers, and basically this is the all solvers we can choose for our purpose. If our fluid is single phase and compressible, or our fluid is a multi-phase with an free surface with only two phases. So if we want to simulate a single phase steady state problems, simple form can be used. On the other hand, for transient problems, if the flow is laminar, we can use incompressible, and if the flow is turbulent, we need to provide turbulent models, and in such case we can use isoform and pimple form. Okay, so what is the difference? So simple form is simple, and piso are two of the most popular and most used CFD algorithms in the industry to couple the pressure and velocity and solve the Navier-Stokes equation. And in OpenFOAM, simple algorithm is only used for steady state problems without the time derivatives, temporal terms. And on the other hand, the piso algorithm is used for transient problems, and incompressible and isoform are piso algorithm solvers. So what is pimple form? Pimple form is a combination of piso and simple algorithm. So I said we only have simple for steady state, and pimple is a combination of piso and simple. So one of the problems about piso form is we need to be very careful about the Courant number, because the solver can blow up if our Courant number is above 1. Okay, but if the mesh is sometimes too refined, or if the time steps if the time span we want to simulate is very long, we want to use large time steps. And pimple is like simple form, it will use relaxation factors to gradually approach the solution for each time step. So it's like the best of both worlds. Okay, for multiphase and compressible, we have LTS interform, which is basically local time stepping, and interform, which is based on the pimple algorithm. So basically, if we cover pimple form, we can solve a lot of problems. And one of the interesting thing, probably a bad thing about OpenFOAM, is its simple form is not very good sometimes. We may have some convergence problems. when the residuals are getting low, but they are not getting lower anymore, and they will stall. Okay, I'll cover these in later videos. Okay, so for our problem, we can see the Reynolds number is 300, so we can assume that it's laminar regime, although it may have some turbulent problems if the surface in reality is rough. Okay, we don't care anymore. We'll assume it laminar, and we can use any one of these. For piezo form and pimple form, we can adjust the turbulence model on or off, okay, to make it turbulence or laminar simulation. In icoform, we have no choice. This is only laminar solver. Okay, so for our problem, I will use pimple form, which can be used for both laminar and turbulent flow problems, and because there is a switch. Okay, and I will use, for now I will only use it as a laminar flow solver. So next step is to choose the numerical schemes, discretization, and solution algorithms. And we have two files, FV schemes and FV solutions, in the system folders of OpenFOAM. And FV schemes include the discretization schemes, especially the temporal schemes, spatial schemes. These are divided into like divergence, gradient schemes, like that, and we will cover it now. And in FV solutions, we can choose the linear solvers or the matrix solvers to solve the linear system after discretization, and we can adjust the inside of these piezo, simple, or pimple algorithms, how many steps we want to use, how much relaxation factors we want to set, etc. So we can adjust such in FE solutions. So let's go ahead and look at these. This is the FE schemes. Okay, and here we have DTT schemes, which is temporal discretization, DTT, and we chose the Euler scheme. This is only first order, but bounded, so I will rather have stability over accuracy for now. And we can use other schemes like Crank-Nicolson for second order accuracy. This is the gradient schemes, and the default is, and probably the best is this Gauss linear scheme. And if we have some problems about convergence, we can limit the gradient terms, especially the velocity terms, using cell limited, or we can even use phase limited, or I forgot the name, MD cell, MD limited, or something like that. Okay. One of the interesting thing is, if we don't know what to use, we can just input a wrong thing, and OpenFOAM will show the right ones to choose from. Okay, for the divergence schemes, and I have chosen the Gauss linear upwind V residue, and this is a second order bounded scheme, and it's stable and accurate. And for turbulence variables, I choose upwind schemes. Actually, now in this step I will not touch the turbulence, because this is only a laminar problem, and I'll consider it later. Okay, now and then we have the Laplacian schemes and interpolation schemes. If the mesh is not good, if the mesh orthogonality is too high, like above 70, we should use something like this. And if the mesh is really good, we can choose linear corrected. Okay, and these SN grids and the Laplacian schemes should be corresponding. Okay. Anyway, I will save and for the FV solutions, we have the solvers. So what are these solvers? These are the linear metric solvers, and for each flow variable. For example, for P, this is the pressure, and we have GMG. This one is quite a useful one, and it's very general, so we can use it for a lot of flow variables, especially for pressure. And we can set the tolerance and relative tolerance, and we can set the smoothing algorithms. And if we choose a Pimple algorithm, we may need to define the P final and U final, etc. These are for the final iteration step for each time step. Well, now we have the turbulence metric solvers, but we don't care about it. And here is the details of the Pimple algorithm. So we can choose the momentum predictor, yes or no, and it's preferably yes for Pimple single phase flows. We just first compute the velocity field, and then we will adjust the pressure again. If we choose no, it will skip that step. Okay, and these outer characters is this one is how many iteration steps we want inside the Pimple algorithm. So if we choose 1, it will automatically switch to Pimple mode. Okay, and here we can see Piso mode, sorry. So if we set 1, this Pimple form will become the same as Piso form, and we can check in the result. And we can choose the non-orthogonal characters, and if the mesh is mesh orthogonality non-orthogonality is high, we may want to choose like higher numbers, like 3. I've already chosen 3, and anyway, maybe it's a bit too much. And we can choose the residual control if we use the Pimple algorithm and not the Piso mode. And these are the relaxation factors. In Pimple mode, the solver iterates until convergence for each time step, and the flow variables are relaxed. But in Piso mode, we only have one iteration step, and it will end. So we don't need relaxation factors for our Piso mode. Sorry. Okay. So that seems good, and now we choose the transport properties inside the constant directory. Okay, and here we can choose the transport model as Newtonian, and the kinematic viscosity can be set. This is meter squares per second, and adjusted to keep the Reynolds number 300. So if we want to crank the Reynolds number, we can use it like the kinematic viscosity of water or something like that. Okay, and then this is the pimple form, so we need to set the turbulence switch. So here the simulation type is set to be laminar. If this is comment out, it will be areas means runs, Reynolds average solutions, and we can choose LES or TES even here. And if we want to use the turbulence model, we need to define which one we want to use, like SST K omega or K epsilon. OpenFOAM has a lot of turbulence models we can choose from, but basically these two are the industrial standard, and it's like everyone uses for both external and internal flows. Okay, so let's look at the control dict. This is inside the system directory, and here this is application in pimple form. It starts from start time or latest time. If we set to start time, it will always start from this start time. And the default is 0. Okay. On the other hand, if we set to latest time, we can OpenFOAM will start from the last time step it wrote the data. For example, we want to simulate like 200 seconds, and we stopped once at 100 seconds, and we want to start from that 100 seconds. We can set to latest time. Okay, for now it's okay, whatever we want. We said it will start from 0 because we don't have any data written. Okay, and this is the delta t. It's important for current numbers, and more important one is the adjust time step. And if we put this yes, it will adjust the time step according to this maximum current number. And just please ignore these guys are for interform multi-phase solvers. Okay, no, this one is okay. And the time step will be adjusted based on this maximum current number and according to the maximum delta t. Even if the maximum current number is much less than 1.0, if the maximum delta t is if our time step is above the maximum delta t, it will reduce the down to this one. Okay, and we can set the write format as ASCII or binary. Binary may save may save a lot of hard drive space, but the ASCII is everyone can read it. Okay. Anyway, the para view will read any one of these. It's okay, and we can choose the write compression off or on. If this is on, the written data will be stored in compressed compressed files like conzip files or something like that. Okay, so we checked everything and seems good. Let's go ahead and run it. Okay, the command is just pimple form here. Maybe it's a bit too okay, I will clean it up. Okay, and let's see. Okay, it's running, but I stopped once. If you want to stop, just Control C or Control C. Okay, because I stopped because I want to check these text, whether everything is good. So okay, it seems the first one it's a bit confusing. Pimple form has been superseded and replaced by more general incompressible fluid solver executed by form RAM application. This is because this OpenFOAM version is too new, so they changed like a few years ago to this format, and the solvers can we don't need to name the solver for a lot of problems. Anyway, I am a little bit old school guy, so I chose to use simple form, and it's universal because this one is like OpenFOAM version 9 or 10. It's equivalent to 9 or 10, and we have another OpenFOAM bloodline. It's V2206 or V like 2006, something like that. They have 4 digits, and this bloodline has only 1 digit, 9, 10, or something like that. Okay, okay, and okay. The more important thing are these lines, and we have create time, mesh, and we choose the solver and compressible fluid, and Newtonian model, and the flow is laminar. And okay, convergence. Okay, the most important one for now is this one, operating solver and piezo mode. So our solver will iterate only once for every time step. Now you can see the smooth solver. This is the about solving the linear metrics for ux, uy, z flow variables, and we see it solved the pressure for 4 times. Why 4 times? Because we said too much probably. Now we have the number of n characters once, and non-orthogonal characters 3. So this is total 4. Okay, and it seems good. Okay, so let's go ahead and run. And the current number it's oscillating because the time step is also oscillating, because OpenFOAM is trying to adjust the time step to keep the current number below 1. Okay, it will work, and you can see the result after that. Okay, for now that's all. Thank you very much.